Welcome back to Week 8, Day 3, 7th grade team. This is Mrs. Allen, the math coach at Bouchon Middle School, and I thank you for coming back to visit with me as we continue learning more about probability. Our weekly learning target is to be able to investigate and describe the difference between the theoretical probability and experimental probability of an event. Today you will need your standard math supplies, your notebook, your pencil, your calculator. Again, you can use your Desmos, the handheld, or even your phone app, and of course, your I Can attitude. Your independent practice exercise from yesterday should look very familiar to you. I'm hoping so because these questions were selected because they were questions that we had actually gone over in our lessons. So go ahead and pause the video, take a look at the answer key, and if there is a particular problem that you are having challenges with, look very closely at the answers, but you can also revisit an earlier lesson for that particular example. When you're finished, please return and we'll resume the video. Today's daily learning objective is to compare the theoretical probability and experimental probability of the same event. Our vocabulary terms for today's lesson are theoretical probability, experimental probability, and compare. This is a reminder of our critical verb compare. When we see the verb compare, it means to find the similarities. Sometimes we will be asked to contrast or to find the differences. It is important to be able to do both. We know that sometimes things that should happen actually do not happen the way we think in the real world. For example, have you seen someone win a prize off a scratch card, feel lucky, and go buy several more? But then they experience disappointment because none of the new ones are winners. It is helpful to be able to work with both theoretical and experimental probability to understand the risk. There are often times when we need to be able to compare these two types of probabilities. We will spend today and tomorrow comparing the theoretical probability of events to the experimental probability of the same event. We are going to start by watching a video clip on what is called risk analysis. Risk analysis is a technique that businesses use to determine what issues could work against the success of their project. Say, for example, you are a business and you want to attract more customers. So you're going to offer a big prize to the winner of a game. You're hoping you don't have to pay it out. Would you offer the prize to the player with the higher or lower probability of winning? Think about it. Why? Questions like these are examples of when we would need to compare experimental and theoretical probability. We are going to watch a video to take a look at Doug McCrum. He's the president of Global Specialty Risks and a risk analyst who examines risks like these for his clients. He predicts the likelihood of winning sporting event contests with probability models constructed from historical data. Let's take a look.
Dead on the hole, dead on. Looking awful good.
Do you think you could make this shot? Would you risk $1 million on it?
Whoa! Hi, Kristen.
Hey, Doug.
Doug McCrum, president of Global Specialty Risk, takes risks like this every day.
Probability assessment and statistical analysis are very important in this type of business.
His company specializes in underwriting contests at sporting events, where fans are given the chance to score a basket, kick a field goal, or hit a hole-in-one, each for prize money.
For all of our clients, they create a promotion or an event for which they specifically hope to have a winner. And for the vast majority of our clients, they can't afford to pay, don't have the resources to pay for the type of prize they want to offer.
Here's what I think.
So my clients turn to me to assume the risk that they actually could incur by setting up this promotion, creating this risk. They contract with me to cover that prize in the event there's a winner. It's our job as a program underwriting manager to determine with some degree of probability the likelihood of the outcome over a series of events.
In order to assess the risk of each contest he underwrites, Mr. McCrum first calculates the probability of an event happening. He does this by analyzing data from similar events that have taken place in the past, looking for predictable patterns that emerge.
In events where there is a great deal of historical data, we compile that data statistically, and from that data, we can then develop a probability model of that event happening.
When there is no historical data, Mr. McCrum has to make assumptions.
If there is not sufficient historical data, then we have to start an assumption process to develop our probabilities.
From these assumptions, computer models are developed that allow Mr. McCrum to calculate new predictions. One probability model he uses is based on a basketball contest, in which contestants are challenged to make a series of 4 baskets: a layup, free throw, top of the key, and half court.
For each individual shot, we assign a probability or likely probability of someone making that shot. In the case of layup, we would say 90%. In the case of a half court, we would say almost 3%, or 1 in roughly 35 shots. For a top of the key, which is the top of the circle, we assign that a probability of 30%. And the free throw, which is at the free throw line, of 50%. To arrive at the overall expectancy, we would then multiply each individual probability, and in this case, it would arrive roughly at 247 to 1.
Because only about 1 out of 247 people selected at random can make this series of shots, Mr. McCrum can accept this risk and offer a relatively large prize without incurring a large fee for the sponsor.
No, it doesn't matter.
Only 1 in 247 people could make the total combination shot.
After developing and testing these models, Mr. McCrum refines them by comparing his expected results with actual results.
We then monitored for actual claim history. It's not the kind of business that you can take a single year snapshot to compare with your probability assumptions. It really has to be done over a 5-year period or longer, such that you get sufficient data.
Without sufficient data, assessing the probability of an event's results can be a risky guessing game.
Most of our cases, from an actuarial standpoint, do coincide with our assumptions. However, when you introduce new product in this industry without sufficient historical data, it turns out that your mistakes can be very expensive in the way of claims. Where we cannot reasonably assess a probability, we prefer not to underwrite that risk.
Deal or no deal? Mr. McCrum shows us that without sufficient data, assessing the probability of an event's results can be a risky guessing game. Betting pools are an example of types of risk you may see on TV or even know family or friends who do them. Probability plays an important role in these games. You may have an idea of the likelihood of winning or losing bets, but remember, our discussion about probability is adding math to it so that we can be more precise and informed in our decision making. There are other interesting ways to think about using historical data to compare probability in the real world. Let's look at some examples. We often hear about recalls on the news. Many times, the companies are not aware of problems with their products. On some rare occasions, some decision makers at a company are aware. Recently, a car manufacturer was caught for a decision it made 10 years ago. It decided not to change a part, thinking that there was a high probability that there wouldn't be any problems. It was wrong. This gamble didn't pay off, and now it is paying huge sums of money to correct the original, less expensive problem. How about Publishers Clearinghouse? We see them on the news and in the mail. It's an opportunity to win a prize that is exciting for many of us. As a matter of fact, when I was in middle school in Pittsburgh, Pennsylvania, I would send back the Publishers Clearinghouse contest entry forms by mail for my grandma because no purchase was necessary. However, it took a lot of time for me to fill out the form, and we had to pay for the stamp. Now, Publishers Clearinghouse contest uses historical data to compare probability in the real world, and it shows them that there's a high probability that most people will not continue through all of these hoops to get the final prize. Let's look at another example that you often see that is related to probability. Well, every few years, we need to get new tires on our car because the rubber wears down from driving. When is the last time that you heard a family member or friend trying to decide where to go to buy new tires for the car? If they are like me, they want quality tires, and they also want to try to save some money. Sometimes retailers offer us a rebate so that we will come to their store to purchase our tires. A mail-in rebate is not an upfront discount. When retailers offer mail-in rebates on purchases, we have to send in the sales receipt to get our discount. Most rebates have an expiration date, and the retailers know there is a high probability that we won't send in our receipt. They are counting on us to misplace the receipt or to take long to send it in to qualify for the discount. How do they know? They use historical data to compare it to the probability in the real world. Here we have a situation where we are examining the theoretical and experimental probability in the same problem. So we know that Erica's flipping a penny 20 times, and she is collecting data on the number of times she landed on a head, and her results are shown below in the table. Which is true regarding Erica's experiment? And if we look at our answer options, they both deal with theoretical and experimental probability in the form of a percentage. So let's go ahead back up and break down our word problem. She's flipping a penny 20 times. And we also see this number 20 down in our table because it shows the different number of flips. She's collecting data on the number of times she landed on a head. So this is important. We're looking specifically at heads for our event. Which is true regarding Erica's experiment? Which is true regarding her experiment? So she has an experiment. Let's start with our experimental probability. The experimental probability of Erica landing on a head is, let's see how many heads we have. So we have 1, 2, 3, 4, 5, 6. And I just want to go back and double check to make sure I didn't miss any. And the ones that are not highlighted are tails. So again, 1, 2, 3, 4, 5, 6. So we have 6 heads. So that'd be our 6 favorable outcomes out of our total number of trials. And we have 20 trials. So 6 divided by 20 gives us 3/10, and 3/10 times 100 gives us 30%. So our experimental probability of landing on a head based on Erica's experiment is 30%. Now let's look at our theoretical probability. And I bet you all have this memorized by now. The theoretical probability of landing on a head, well, how many heads are there on a coin, a fair coin? It's 1 head out of 2 total possible outcomes. 1 divided by 2 gives us 5/10, which is the same as 50%. So these are our 2 probabilities that we're looking at. So we have 50% is our theoretical probability of landing on a head, and 30% is our experimental probability of landing on the head. Now let's look at our choices to see which one of these choices are applicable to our experiment. So first, the theoretical probability is 20%. We know this is not correct because we calculate the theoretical probability is 50%. The experimental probability is 40%. And that's not correct either because we calculated it at 30%. The theoretical probability is 50%. Here we go. This is true based on our calculations. The experimental probability is 30%. Yes, this is true, also based on our calculations, and we still want to make sure that we go through all options to make sure we don't miss any. The theoretical probability is 60%. This is false, because we said the theoretical probability is 50%, and the experimental probability is 20%. True or false? That's correct. This would be false as well. So we have two answer choices regarding Erica's experiment. I want you to try this problem on your own. Pause the video, and when you're finished, return, and we'll continue. Let's see how you did. So for this question, we have several students who conducted a simulation where a coin was tossed several times and they recorded their results. Which table shows an experimental probability of landing on tails as greater than the theoretical probability? So we're comparing two probabilities. So what we need to do for each of our answer choice options is we had to identify the probability of landing on tails. And our formula for that probability is the number of favorable outcomes divided by the total number of trials. And so when we look at the two probabilities, we see that for letter C, that 24 times it landed on tails out of 46 total possible outcomes, which is approximately 52 hundredths or 52%. In this case, that would be the only example that shows a greater outcome than the theoretical probability of landing on a tail, which is 50%. How did you do? Again, our learning objective for today was to compare the theoretical probability and experimental probability of the same event. As we have seen in today's lesson, probability comparisons take place all around us. Think about it the next time you hear the news report about a recall, or when you see the sweepstakes come in the mail, or even when you need to remind Nana about sending in her mail-in rebate to get her discount. So it's that time to reinforce the content from today's lesson. For your independent practice work, you're going to complete week 8, day 3 in your learning plan. Remember to show your work and annotate. Once you're finished, you will strengthen your math skills by completing 2 Dreambox lessons. And now for our future connections. Today's learning objective was to compare the theoretical probability and experimental probability of the same event. Tomorrow, we will continue working on this same objective. Remember to share your avatar and upload your probability experiment to share with the team. Both of these links to the Padlet are found in your learning plan. Have you taken a peek, perhaps to see who else might have uploaded some items as well? It's worth a look. And I thank you for being my learning partner today. Be safe. I look forward to seeing you tomorrow. And remember, make today so awesome that yesterday gets jealous. Have a great day.